So we are done with the process of sketching the body diagram of a given problem. Now at this point, we are to proceed with the more like the second step for solving problems, and that is where we create the summation of forces. So basically, at this stage, we are now writing equations to describe the forces that act on our system. Now, the guiding principle that I would like you to remember on this one class, and this will be formally discussed in a separate discussion, is that whenever we take the summation of the forces that is represented by that symbol over here, this means the sum of. So the sum of the forces is equal to mass multiplied by the acceleration. So as I said, this is probably quite familiar with you, but we have not formally discussed this yet in the class. So this is actually derived from um, Sir Isaac Newton's second law of motion. So as I've said, we have a separate discussion for this one. Now, why I mentioned or introduced this one, because in the this step of the problem solving involving Newton's laws, this will be our guiding equation and foundational equation that we will be utilizing, as you will be seeing here. Okay. So also we are still dealing with the same problem that we had in the free body diagram, problem A, B, C, and D. And if you still don't understand or are a little bit confused as to why the free body diagram of the problem looks like this one, feel free to check the posted videos on the explanation on the free body diagrams, why it looked like that. Okay. So when we take the summation of the forces also class, we take the summation of the forces per given body. It means to say that we take the summation of the forces. In this case, we write summation of forces on 1. Okay, and I'm hoping you also realize that in taking the summation of the forces, you are actually going to utilize the free body diagram that you have used. Okay, so first, I'm gonna write in blue. First thing that you should remember is you use this form, the sum of the forces, and you have to indicate the subscript. That means I am looking at the x component, so that's why I have a subscript x here. I'm hoping you are seeing that. So the sum of the forces in x is just equal to, sorry, is just equal to the mass multiplied by the acceleration along x. Now, let's try to break down the components of this equation first. So the mass in this case here is the mass of the ring in the problem, because your forces, if you remember, are interacting on this body over here, which is your ring. So the mass there is the mass of the ring, and then your AX, this one over here, is your acceleration of what? Still the ring. Acceleration. This is of the ring, and this is also of the mass of the ring. Right? So one of the things that you should remember then is that in this equation, the sum of the forces along x is equal to max. The m that you are referring there will always be the mass of where you are getting your free body diagram. And then the acceleration is the acceleration of that mass where you are getting your or sketching your free body diagram. So in this case, for body 1, we are talking about the ring where the three forces are actually interacting. The forces, namely T1, T2, and T3. So when you take this equation over here, that means that the masses and acceleration of that are referring to the ring. Okay, so that holds true also for other na mga examples, as you will see later. So the second step that we have to do over here is to simply, and this is more like a practical tip on how to do it. You write the sum of the forces in x is equal to MEX. So what are then these sum of the forces on x? So to answer that, you need to look at your free body diagram. Therefore, it's really crucial that you have the correct free body diagram. So for all the forces on x, you simply look at the forces found on your x component or on your x-axis. The first force being T2, since that is on your x. By the way, it should have x over here. You define this as your x-axis, and this is your y-axis. So T2 being the first one over there, and since it's directed towards the left, so you have negative T2. All right. What are the other force on x? So you have this one, the T3x. So you are going to write plus T3x. T3x. Now, if you are wondering why we denoted it as plus T3x, I am hoping you understand why. So since it's found on the x component na right hand side where the x are actually positive, that is why the value of your T3x is positive. What are the other forces that can be found on the x-axis? So clearly, those are the only two forces that are found on your x-axis. So you equate it with MAX. All right. So take note that this T3x has components, if you remember, right? It has components. So how do we get the component of T3x? So simply you recall from our previous discussion, negative T2 plus, I'm just gonna write over here, T3x. So this is what we want, right? That T3x there. So how do we get that? Now take note that this is already in 60 degrees. So if you recall from our previous discussion, we have, I'm just going to define some x and y axis over here, and I'm gonna erase it later. So if you have this as your force T3, I'm hoping you can recall this discussion, and you have an SPA of 60 degrees. Take note, class, that this has T3x and T3y. So ganito itong nadamdaman. So we recall, or we hopefully recall from our discussion, that the first component of the T3 will just be some T cosine of theta. The second component being T sine of theta. Now maybe what you are familiar with in our class, since we are using this one, is if you have vector A, this is vector T, you have a cosine theta and a sine of theta. Now, of course, the theta are measured in SPA, right? So that's really the condition for this to hold. Now, in this case, for T3, I would like you to try to check out T3. And T3 is right over here. You can see that. Okay, I just did something, so I just had to undo that one. Okay, T3 is over there. So T3 also, if you want to get T3, that is the first component. So basically, you will just get from this one, T, I have red. This is just T cosine of 60 degrees, since 60 degrees is the angle theta in that case, is equal to MA sub x. So basically, this is your equation from along x of free body diagram 1. However, you have again, you can actually further simplify this one, class. Take note that the ring in this case is stationary. So it's not moving while the three forces are acting. So that implies that the acceleration is 0. Because there is no motion, the acceleration is 0. So this one over here is 0. So your equation will be reduced to negative t2 plus t cosine of 60 degrees. By the way, this is t3. T3 is equal to 0. So you name this as your equation 1. So that's it. You actually have solved already for the first equation for body 1. Now, we're still dealing with the same body. Let's take the summation of the forces along y. So we will still utilize the same equation. We write it like this one. The sum of the forces along y is equal to m. Take note, this will be a sub y, meaning the acceleration along the y-axis. Now, what are then the forces along y? So you look again at your free body diagram and you see T1 is over y. By the way, I'm gonna use another color just for emphasis. So T1 is one of the force and it is directed downward, so on the negative y-axis. So you write negative T1. What are the other force? The other force is T3y, right? So since it's on the positive y-axis, so you have plus T3y is equal to m a sub y. Now we have no problem with negative T1, so we copy that one plus, how about T3y? So T3y is right over here, and we want to get the component of that. So we simply recall from our discussion that when you have a vector t and it has components, do note that as long as the angles are measured in SPA, just like this, once it's measured in SPA, automatically the x component or the first component will be cosine of theta, and the y component of that will be the sine of theta. The x component, cosine of theta, sine of theta. So in this case, building up on what we just discussed from the sum of the forces along x, I'm referring to this one, your T3y will have to be T3, the sine of theta. Kasi nga, ito siya. This is T3y, the second component. So that is clearly sine of theta. So that's why you have T3 sine of theta. And then this will be equal to m a sub y. Now, the next question, is there any acceleration along the y-axis? Or is the ring in this matter, moving along the y-axis with an acceleration? Clearly, it's not moving because it's static. So, that implies that the acceleration is just 0, thereby simplifying further our equation into negative t1 plus t3 sine of theta is equal to 0. So that is your equation 2. Alright? So that's just how easy it is to take the summation of the forces by setting up the equation. Now, finally, we are on body 2. So let me just zoom in over here. So the equation or the sum of the forces for body 2 will look like this. The sum of the forces, let's start with x. By the way, this is the sum for, I'll just write for body, all right, 2. So the sum of the forces along the x, guess what? It's equal to max. Well, I have an equation for this. Now, again, the key for taking the summation of the forces is the free body diagram. If you look at the free body diagram, you are seeing no force along the x, right? This direction, there are no forces existing over there. It means to say that you have to write that the sum of the forces along x is equal to 0. You don't have to go through that one. Or if you would just like to write, then write it. The point that I'm trying to make there is that there are no forces on the x component with respect to body 2. Now, how about the y component? So we continue. The sum of the forces along the y-axis is equal to m a sub y. Now, if you notice, class, kinibitaw akong ipang ano, this one and this one, these are very central equation. Dira kita always magsugod sa atong summation of the forces. Okay? This one, I think I've mentioned it inina, kana sila, dira gyud ta magsugod pinaka first gyud nato na nga i-write after or kung magkuha sa sum of the forces. And that is just your Newton's second law, and as I've said, we will have a separate discussion for that. Okay, so for this case, let's go back to our summation of the forces. Take note, focus your attention now on the free body diagram number 2, since this is a problem, or we're taking the summation of the forces on 2. So the first force that you are seeing clearly is T1, right? And its direction is upward. Therefore, it must have a positive sign. So T1, positive, and then you add. Basically, you're taking the sum of all the forces. So you add the force along the y-axis, which in this case is W, or the weight. So the weight is just, by the way, the weight should bear a negative sign since it's on the negative y-axis. So plus negative W is equal to m acceleration along the y-axis. So further simplification will have this. You have T1 minus W is equal to mass acceleration along the y-axis. So you have to remember always, class, that the equation for your weight is just the mass of the object multiplied by the acceleration due to gravity. And this is 9.8 meters per second squared on Earth. So you have to remember that one because you have to substitute that in your equation. So you have T1. So this will become T1 minus M multiplied by G is equal to M A sub Y. Now, again, sa ganito, si A sub Y, we ask ourselves, what happened to A sub Y? Now, take note of this problem over here. Is this engine in any way accelerating downward? And the answer is no. It's static. It's only hanging there. It's not moving downward at all. Therefore, that is telling you that the acceleration along y is 0. This one over here is 0. So your equation is simplified into T1 minus mg is equal to 0. So you name this as your equation 3. Okay, so that over there is, or are, your summation of the forces.